Hi, so today we're going to be proving the fundamental theorem of calculus, or this infamous expression over here. So the fundamental theorem of calculus is one of the most powerful tools that we have. It gives us the area under a curve on a given interval. What I mean by that is, let's say you have a curve which models the function f of x, and then you have an interval on point A and point B. What the fundamental theorem of calculus gives you is the area under this curve at this given interval. It has various uses in geometry, physics, economics, and a lot of other fields. But what it claims is, to write it down mathematically, it's already given here, but I'll write it again. The area under the curve of f of x on the interval a to b is equal to big F of x evaluated at the points B and A. So big F of x and small f of x are obviously related. This is where it joins the definite integral and the indefinite integral, the fundamental theorem. So what this means is the indefinite integral of small f of x is equal to big F of x. So the derivative of big F of x is equal to small f of x. So to prove this, we're going to be creating another function with a dummy variable. So because we're going to be using the variable x for another reason. So let's say you have a function a of t, which gives you the area under the curve from some point a to some variable point x of the function f of t, which is the integrand, and dt, which is the variable we're going to be integrating with respect to. So by definition, if we prove the statement d over dt of a of t is equal to f of t, we'll be able to prove the statement. We'll be able to prove the fundamental theorem because a of t gives you the area under the curve of f of t. This is all going to make sense. Just give it a second. So let's say you have the function f of t over here. Just hold that thought for a second. This is the function f of t. So to prove this statement, we have to go back to the definition of a derivative. So the definition of a derivative goes, it's the limit as delta x goes to 0 of a of x plus delta x minus a of x over delta x. So now what we have is an extremely convoluted expression, which we're going to have to simplify if we're going to have a prayer to prove this equation. So let's say this is the point x, and this is the point x plus h, or x plus delta x. So we can tell that x plus delta x is equal to x plus h. So h is equal to delta x. This is important. So what if a gives the area of the function f of t? What this means is a of x plus delta x is this area over here. We go to another color. We switch the color out. And a of x is the area over here. So a of x plus delta x minus a of x is this area over here. So if we have to blow this image up to make it more comfortable to see, if we have to blow this image up, you get something that looks kind of like this. So this is equal to this. So we all know that the base is equal to delta x, and this is a of x plus delta x, and this is a of x. So if we have to draw a rectangle to show the width of, to show the area of this shape over here, let's say we have a rectangle which is of height a of x plus delta x. The rectangle, it's clearly seen that the rectangle is too small. and does not depict the area properly. But if we have the area that starts at a of x, it's too huge. So we need a point between a of x and delta x. So we need a point b, which was greater, b is going to be greater than a of x plus, my bad. B is going to be between x and x plus delta x. Let's call this point B x hat for convenience purpose. So the area of this over here is delta x multiplied by f of x hat. So we can replace this equation over here with this one. So what you realize is it's the limit of, as delta x goes to 0, of delta x multiplied by f of x hat over delta x, and the delta x's cancel out. So it's the limit of, as delta x goes to 0, of f of x hat. So what you realize is this is delta x over here. As delta x goes to 0, b, or x hat, is between x and x plus delta x by definition. So as delta x goes to 0, x hat tends to delta x hat tends to x. So the limit as delta x goes to 0 of this equation is equal to f of x. So now what we've done is that we've proved that the derivative of a of t is equal to f of x. A of x is equal to f of x. The derivative of a of x is equal to f of x. This is what we've proved over here. And since a of x is the area function, the fundamental theorem of calculus holds true. And since we know the integral of any, the indefinite integral of any function is accurate up to a constant, and it's a form f of x plus c, this will be the integral from a to b, or the area, which we just proved, will be f of x will be equal to f of x evaluated at b and a. And the reason that we don't consider the c, or the constant value, there's multiple reasons actually, but I'll give you one good one right now. Let's say we had plus c over here, so equal to f of x plus c evaluated at b and a. What evaluated at means it's f of b plus c minus f of a plus c. So what this means is, if we had to evaluate this expression over here, you'd get f of b plus c minus f of a plus c. So c's cancel out. So you'll basically get f of b minus f of a. And this happens every single